my esteemed viewers. In this tutorial, we will continue with the friction problems, and specific to this particular tutorial, it is the coverage of friction forces that would develop on horizontal planes. And friction problems are friction that would develop on horizontal planes depends upon the system. There is a block over here, there is another supporting surface, and there is a force that is being applied over here. It is the horizontal, and there may be a force going like this. Then this particular block would try to slide rightwards, and accordingly the friction will be developed, frictional force will be developed underneath this particular block in reversal of the direction of the tendency of the external forces, opposing the external forces. The system may be like this, or system may be like this. There is a block over here connected through the wire or a thread or a rope to a weight over here, and as the weight increases beyond the capability of this particular weight, this particular block tends to slow some kind of a sliding towards right, and accordingly the frictional force will be developed on this horizontal surface in a reversal fashion. And here is the person who is trying to push this particular big block in this direction, and accordingly the frictional force will be developed on the horizontal floor in a horizontal direction, opposing the tendency to this particular block being pushed. And here is a rack and pinion adjustment, and here there is a lever, and there is a wheel which is showing some kind of a rotational tendency, and this is the force that is being applied, which will have a braking effect on this. If this wheel were to turn in clockwise direction, there is a tangential frictional force which will be developed in the direction shown, that is in the direction leftwards. Here is a rack and pinion adjustment, and a force P which is applied in this fashion will make this particular rack and pinion adjustment to slide rightwards. Therefore the frictional force will be developed in the horizontal direction leftwards. And in a real world scenario, there is a person who is pushing this particular big container containing huge weight in the horizontal direction, and the force will be acting in an inclined fashion, and there is a horizontal component of this force which is along the movement, and there is a vertical component also, and this horizontal component will definitely try to pull this particular huge weight in the horizontal direction. At the contact surfaces with the tire, there will be 4 frictional forces, one here, one here, one here, one there, along beneath all the wheels, tangential to these wheels, and it will be in a horizontal plane. And here is another person who is trying to push this cupboard, and there is a frictional force that is being applied, and there is a force that is being applied in order to push this cupboard in the rightward direction, or almirah in the rightward direction, and accordingly there will be a frictional force that is developed. While this particular problem presents a kind of a non-concurrent force system, because one force is there, another force is over here, and the entire system can be represented on a two-dimensional Cartesian coordinate system or two-dimensional plane. But here this problem also comes with a danger that this particular cupboard, since the force is applied somewhere at this particular height, may have a tendency to rotate with respect to this particular corner. Anyway, we will go by examples in order to reinforce our understanding on this particular kind of problems. The question here is, what is the force P required to cause impending motion between block B and ground? It is not between block A and block B. It is between block B and and the ground. And here the frictional coefficient happens to be 0.4, and here it happens to be 0.25. And we need to write in any friction problem, as a matter of fact, it is always advisable to write the free body diagram of the body which is tending to show some kind of a movement in any direction, as a matter of fact, due to the applied force. Then the writing of the free body diagram of the other part of the system will becomes very easy. Therefore, in that particular context, the free body diagram of the block A is written. There is a force P over here. 100 kilonewton is the weight which is acting vertically down, and since this is showing a tendency of the movement in the rightward direction, there is a frictional force acting in this direction, and there is the normal reaction N1 for A, and this we need to resolve the forces, of course, and we will just do this. Block A is in equilibrium. Then P will come with a component. This is P cos theta, cos 20 degree, and this is P sin 20 degree. And this is the free body diagram of A. Then we will apply, since the block is in equilibrium, our block can be assumed to be in equilibrium because it is just showing tendency for some kind of a movement, horizontal movement. It is called as impending motion. Motion has not yet happened in a full scale. It may show off in the form of a jerk in horizontal direction. That is good enough to say that the block is still in equilibrium, and if the force exceeds beyond a particular range, this block will start moving and it becomes a problem of kinetic friction. Sigma fx equal to 0. Algebraic sum of all the horizontal components will be equal to 0, and it comes P cos 20 minus 0.4 N1 equal to 0, because these two are the only horizontal forces, and we will be able to develop some kind of a relationship between P and N1, which can be utilized very usefully in some other equation in order to resolve the unknowns. And sigma Fy is also equal to 0. That is, algebraic sum of all the vertical components of the forces should be equal to 0, and that will enable us to write N1, which is going upwards, positive, and 100, the weight which is coming down, negative, minus P sin 20, this is the component, and N1 minus 100, and we will replace this P by 0.43 N1 from the equation number 1, and sin 20 will be there equal to 0. And with the solution of this particular equation, we will be out with N1. So N1 happens to be 117.23 kilonewton, and therefore P can be calculated to be 0.43 into N1, that is 50.49 kilonewton. Now, since the question, this force required, this is the force which is required to cause impending motion between top and bottom blocks. Now, we will write the free body diagram of the bottom block. It has a weight of 200 kilonewton, which is acting down. N2, this is the reaction offered by the floor to this particular block, and this is also showing a tendency to move in this particular direction. The frictional force will be like this, and we should carefully watch the direction in which we have written the frictional force. In the earlier case, we have written the frictional force like this, and at the interface between and the frictional force that is developed on the top of the block B, owing to this particular force, will be opposite to this. So when we unite these two blocks, this frictional force and the other frictional force will cancel away. This frictional force will cancel away, and it would seem as if both the blocks are in equilibrium at the interface. This is the analogy, and this is the reaction coming from the top block towards the bottom block. That is 117.3 kilonewton that we have identified, and this is the frictional force between exerted or generated due to the relative movement of the block A against block B. Okay, and this is 0.4 times 117.3, that is 46.9 kilonewton, and this is the weight, and this is the frictional force which is due to this. And when we write this, we look at this. Okay, as far as this block is concerned, the tendency of this block to move in this direction is owing to this. Therefore, we have written the frictional force opposing this particular frictional force, and this will become the tendency, this will become the external tendency to push this block in the rightward direction. So this becomes 0.25 N2, and this is N2, and we will assume that block B is also in equilibrium. Okay, sigma Fy equal to 0. Therefore, that will enable us to write N2 minus 200 minus 117.3 equal to 0, and that will give us N2 equal to 317.3, and frictional force will be 0.25 N2. So 0.25 into 317.3, 79.32. So when we go back and when we see the value of P happens to be 50.5 kilonewton, which is much lesser than 79.32 kilonewton, which is developed at the bottom of the block B, which is sufficiently high enough when compared to the external agency, external force, that is 50.5 kilonewton. Therefore, we cannot expect any impending motion between the block B and the floor. Example number 2 goes like this. There is a block over here. There is a thread that is being carried over this pulley, and there is a weight that is being hung. And the frictional coefficient between this bottom block and this top block happens to be 0.35, and the question is, what is the weight required for this particular block which is hung over here for impending motion that should be caused to this particular block? And top block is in equilibrium because it is an impending motion, and here I have written the tension in the wire to be W. And it is very important to remember that a thread or a wire or a rope cannot be subjected to compression because it is flexible. And in order to identify the amount of tension that is acting over here, we will just assume the weight of this block to be W, and you have to make a small cut over here in order to analyze the equilibrium of this particular block. This particular block is not going down because it is being held by the tension force that is being developed, and tension equal to W. Because if we just apply sigma Fy equal to 0 over here, tensional force which is going like this and weight which is acting downwards has to nullify, and we will write T which is positive going up minus W equal to 0. That will enable us to write T equal to W, and it is this W which is acting all along the wire in the form of tension. Therefore, here is the free body diagram. There is the top block 700 Newton acting down, and weight, the external force, and 0.35 Newton, that is the frictional force, and this is the normal reaction offered by the bottom block towards the top block. And we write now we will develop the equation sigma Fy equal to 0. So it should be definitely n minus 700 equal to 0, n equal to 700 Newton. Therefore, the frictional force will be 0.35 N, sigma Fx equal to 0. Okay, it is W, that is sigma Fx equal to 0, that is W, positive going right, minus 0.35 N equal to 0. So W equal to 245 Newton. So 245 Newton is just enough to cause some kind of a instability, some kind of a jerk in horizontal direction as far as this block 700 Newton is concerned. So we will take up example number 3. For the arrangement of the block shown in figure, find the range of values of theta for which block A will not show impending motion. So this is theta, and in order to find range of theta, this is called as angle of elevation. The the thread is held high above this horizontal axis, and it is passed over the pulley, and a weight is hung. This is 400 Newton, this is 700 Newton. It could have been arranged in this fashion also, right? Here the thread goes, or the wire goes, or the rope goes with an angle of depression. This is angle of elevation, and this is angle of depression, and the arrangement could have been like this also. Therefore we will find the value of theta in this direction, anti-clockwise direction, and value of theta in clockwise direction, and we will just say that as the range. Okay, and for this we have to take the first case where the wire is being tied with an angle of elevation, and this is the direction of the motion, whether it is angle of elevation or angle of depression. And this is the free body diagram of the block A, 700 Newton, and this is the normal reaction, and this is the frictional force, and this is 400 Newton, which comes like a tension, and Fx equal to 0, sigma Fx equal to 0. That will enable us to write 400 cos theta minus 0.35 n, that is the frictional force, equal to 0. So we will have some kind of a relation between n and theta. So n equal to 1142.85 cos theta, and this is the component. Sigma Fy equal to 0 will enable us to write 400 sin theta, that is going up, plus n, which is also going up, minus 700, the weight which is coming down somewhere over here, and we will develop an equation. Now 400 sin theta will remain as it is. N is replaced by this particular relationship gotten in equation number 1, and minus 700. That will give us, by trial and error, we should start applying value of theta, say from 10 degree, and we have to incrementally increase the value of theta, so that we will almost appear to 0 value. So it so happens that if we substitute theta equal to 74 degree, the equation will tend to become 0. So that is the angle of elevation. So as far as angle of elevation is concerned, it goes from 0 to 74 degree, okay, up to 74 degree in anti-clockwise direction. So when we consider the rope making an angle of depression, something like this, the free body diagram doesn't change too much, because the tendency to draw this block is always in the rightward direction. Therefore we will apply the equations of equilibrium. Sigma Fx equal to 0, that will give us 400 cos theta in rightward direction, minus 0.35 n equal to 0. Therefore n equal to, this is the relationship that is obtained, and sigma Fy equal to 0. That will give us minus 400 sin theta, which is acting down. Yeah, I will try to write this for the sake of clarity. This is 400 cos theta going like this, and this is 400 sin theta, which is coming like this. Okay, and you should notice over here, this 400 sin theta will add to the weight. It will add to the weight. So minus 400 sin theta, it's here, plus n, which is going up, minus 700, the weight of the block, equal to 0. So that will give us, and we will replace n by 1142.86 cos theta, as we did earlier, in the similar fashion, of course, by the trial and error method, and theta happens to be 35.4 degree. 35.4 degree. It cannot go further, because it will add to the weight. It will become 400 only if this theta becomes 90 degree. Therefore when theta moves from 0 to 90 degree, sin theta keeps on increasing. As far as angle of elevation is concerned, it is 74 degree. Okay, we can go up to 74 degree because with the force which is going with angle of elevation, the sin theta will also, the vertical component will also vertically upwards, and it will give a relief as far as the weight is concerned. So it acts like some kind of a buoyancy, therefore this weight, the weight of the block will get which will get relieved to certain extent. Therefore it doesn't take too much of a force to pull this. The component of what I mean to say is the vertical component of 400 Newton will reduce to some extent the weight of the block, since the frictional force is directly proportional to the normal reaction, and the internormal reaction is related directly to this particular weight. The effort required will also be a little lessened. Okay, and we can lift this particular thread to 74 degree. As far as angle of depression is concerned, there is a limit, because it goes on adding to the weight, and if the weight is increased due to this particular vertical component of 400 Newton, it generates tremendous amount of friction. Therefore we need much greater effect in order to pull this block rightwards. That is the learning that happened in this particular problem. So if at all we want to apply the force, it is by intelligent way, by intelligent thinking, we can apply the force with a little angle of elevation, because the vertical component of that particular force will reduce the weight of the body to some extent. Therefore the normal reaction developed at the bottom to some extent. Therefore the frictional force will also be reduced. So in example 4, we will look at a problem which has a figure which shows a cupboard of 500 kilonewton weight. A force of 200 kilonewton is applied at 0.8 meter vertically from the bottom. Will this force slide the cupboard to right? That is a question. Also verify whether the cupboard will tumble, tip or rotate. This is the question. Let us see. First of all, we will write the free body diagram of this, and we will note the dimensions of this particular cupboard, and we will just go solving this. Right, and here is the cupboard. 500 kilonewton is acting, and here is the force that is being applied. It is the horizontal component, and this is the vertical component of the applied force. Since this cupboard shows the tendency to move rightwards, there is a frictional force that is being developed leftwards, and this is the normal reaction developed at the floor, and the cupboard is in equilibrium. Therefore we will write sigma Fy equal to 0, n vertically up, minus 500 vertically down, plus 200 sine 20. This is angle 20 degree, this angle is 20 degree, and this is 200. We will write it down. This is 200, yeah, 200, and this is 20 degree, yeah. Then this force is 200 sine 20, and this is 200 cos 20, yeah. Now the sliding force will be equal to 200 cos 20, 187.93 kilonewton. The frictional force equal to, that is developed over here, equal to 0.25 n. So 0.25, 431.6, 107.9, and the sliding force is 187.93. Since the frictional force is less than the sliding force, the sliding force is 187. The tendency, the force with which the force that is applied is 187.93, which comes as a component of 200 kilonewton, which is being applied with little inclination with respect to horizontal. Since F is less than sliding force, the cupboard slides. Okay, the sliding force F, the frictional force that is developed is less than the applied force. The cupboard will definitely slide, because this is going to outsmart the frictional force. Right. Verification for tipping. So tipping means rotation. So this is the block which is being pushed from the back, let us say, and this particular point is called as toe. This particular point is called as toe. Okay, this particular point is called as toe. Then this point is called as a heel. This is heel. Heel. When the force is applied, if at all it has to tip. If at all it has to tip. And tipping happens typically due to the moment generated by this force with respect to this particular moment center. I repeat, if at all this particular cupboard has to rotate or to tip or to tumble, it has to tumble with respect to this. And the disturbing forces are this and this because they generate moment with respect to this particular point. And of course, if it is not rotating, the reason is this weight, the gravity, the self weight of this cupboard. And as far as this self weight is concerned, it can also rotate in anti-clockwise direction, rotation in anti-clockwise direction with a moment arm equal to 1.2 by 2. As far as these forces, this force has a moment arm of 0.8 and this force has a moment arm of 1.2 meters, the width of the cupboard. Okay, and let us see what would happen. And when it tips, it will just become like this. It will rotate like this, and you should see over here when it just makes a tendency to tip, the entire cupboard will lean. When it leans forward, it loses its contact with the bottom, with the floor. Therefore, there won't be any reactions. Reactions will become vanished. There won't be any reactions offered by the floor because there is no contact at all. But anyway, this will be there. These forces will be there because they are the causative forces. And the restoration, if at all it is not rotating, it should be done by this particular force because this is generating anti-clockwise moment, this is generating clockwise moment. Now we will take moment. Tipping rotation will happen about this particular edge. Anyway, this is 0.7 meter. Yeah, this is point. Yeah, okay, we will change in the original figure itself, right? Anyway, we'll go back and change it. That's better. I think we wrote 1.2 meter. Yeah, as far as the dimensions are concerned. Yeah, 1.2 meter. We will make it 0.2, or we will, yeah, we will make this as 0.7 meter. I don't know why it has changed, sorry. Anyway, point sigma Fy equal to 0, n minus 500. Okay, all these things are explained. Yeah, this is about tipping. We have come here. Okay, moment causing the turning or rotation tipping, 200 cos 20 into its moment arm. It's a 0.9. 200 sin 20 into 0.7. 200 sin 20 into point. This is the moment arm with respect to this. So we may assume this may not seem to be a perpendicular distance or let us say moment arm because it is showing some kind of a tipping. But anyway, you should assume, we should assume that it is a slight tendency. That's all. Still contact is not there. That's all. Because we want to, we should consider the fact that there won't be normal reaction because it may be an air gap, let us say, air gap. So 200 cos 20 into 0.9, this is the height. 200 sin 20 into 0.7, this has a moment arm till here and this has the moment arm till here, and equal to, yeah, that when we accumulate this, it is clockwise 217.02 kilonewton meter, exclusively generated by these two forces. And if at all it has to stand by stability, moment that provides stability against rotation or restoring moment, which is due to weight of the cupboard. Okay, the cupboard weight will offer some kind of a protecting moment or stabilizing moment or restoring moment. It has a moment arm equal to 0.7 by 2, that is 500 into 0.35, that is 175 kilonewton meter. So we will quickly go and change the dimensions. Okay, right, in the original figure it's over here. Yeah, yeah, this is the figure. We'll make it as 0.9 and this is 0.7. Now, yeah, right, we will just continue. So we covered example number 6, and yeah, these are all the things. So we need to take moment with respect to toe, not with respect to heel. And if the cupboard is replaced by a person, we will have heel over here, we will have toe over here, and if you are pushed from the back, we are going to tumble upon, or we are going to fall on our face to the ground, unable to sustain the moment that is generated at our toes. As the tipping moment is greater than the restoring moment, tipping will also surely happen. So this cupboard will also slide, show the sliding tendency, and it will also show some tipping tendency or rotation tendency. The door, a door weighing 200 kilonewton, example number 5, 200 kilonewton is to be slid by means of force P. This is the force P, and this can move with respect to this rack and pinion adjustment. Two runners at A and B, this is A and this is B. Mu is 0.25 and 0.35 respectively at A and B. Here the friction between this rotating wheel and this rack is 0.25, and this wheel and the rack is 0.35 at A and B respectively. Now we will write the free body diagram. This is the reaction RA, this is the reaction RB vertically, and this is the distance between the supports. Yeah, the wheels can be taken as supports. Since it has to show the tendency to move to rightwards, and here is the frictional force 0.25 RA, because the frictional coefficient over here is 0.25 and here it becomes 0.35 RB, and there is a weight acting over here. So the system is acted upon by the reactions, the frictional forces, the weight, self weight, and the tendency to push this to make this particular gate to move in the rightward direction. We will, at the verge of sliding, the door will be in equilibrium. That will enable us to write sigma Fi equal to 0. So RA plus RB equal to 200. Now sigma Fx equal to 0 will give us P equal to 0.25 RA. This is this frictional force plus 0.35 RB, which are negative. Therefore, it can be said that P equal to 0.25 RA plus 0.35 RB. Right. Sigma MB equal to 0, because we have three unknowns. P as an unknown, RA as an unknown, RB as an unknown. So we need three equations to solve this, because this particular problem presents an example of application of non-concurrent coplanar force system. So if we take moment with respect to B, RA into phi, the clockwise direction. So it is clockwise direction. Yeah, RA into phi has a clockwise directional moment, and P into 7, it has anti-clockwise directional moment. Yeah, and 200 into 2.5, and 200 into 2.5, it will also have anti-clockwise effect. Okay, the anti-clockwise effect or clockwise effect comes from the direction of the applied force, so it has to rotate like this, and because this is the moment center. Okay, as far as this is concerned, it has to rotate like this, because this is the moment center. Okay, like this we have to decide, and this is it has the arrow somewhere over here, it is going like this, and this it will rotate like this. It's a clockwise moment. Okay, so by looking into the tip of the arrow, the sense of the force rather, we can decide whether the moment generated or going to be generated is clockwise or anti-clockwise. Yeah, now we will solve this. Okay, now 5 times Ra, we are substituting, and we are removing this particular force P by means of this equation, and we will also remove now Rb, because this is obtained from equation number 1, and we have only one unknown when we took sigma mb equal to 0, and we will be able to solve for Ra. So when we solve for Ra, we will substitute this back to our equation number 1. We got Rb. Then we will just apply the known values of Ra and Rb to the equation number 2, which has related Ra and Rb in terms of frictional coefficients. So P happens to be 52.63 kilonewton. So 52.63 kilonewton is just enough to create some kind of a jerk, some kind of an instability, some kind of an impending motion to rightwards of the gate. So example number 6. The force required to break the impending rotation of the shaft is 65 kilonewton. 65 Newton. It's over applied. This is a brake arm or lever, whatever you say, and it is supported over here. And this wheel, which is being controlled by this particular arm, this particular brake arm or lever, is trying to rotate in clockwise direction. So the impending rotation by this particular shaft is in clockwise direction, and it has a height of 1.5 meter from this support, and its radius is 0.8 meter, and this arm, this lever, has a width of, or a height of, a width of 0.7 meter, or the thickness of 0.7 meter, or the height of 0.7 meter. The friction between this rotating wheel or shaft and the brake arm is 0.4. We will just quickly write the free body diagram. This is going to generate a vertical reaction here, and there will be a frictional force. Since it is rotating in clockwise direction, there will be a frictional force which is tangential at this particular point leftwards, because it has to generate anti-clockwise rotation. And here there is a reaction coming from the top, from this support, and we will just name them. This is A, this is B, and this is C. Here there is a wheel, okay, and this is the brake lever, and here there is a vertical reaction coming from the wheel, and this is the frictional force. This is the frictional force which is acting in this particular direction as far as this block is concerned, because this is trying to rotate like this, so it will experience a frictional force in the leftward direction, and this is the reaction offered by the braking arm to this wheel. This is the reaction of vertical reaction offered by the braking arm to the wheel, and this is the frictional force opposing this rotation, because if you take moment with respect to center, this will create anti-clockwise rotation. So the clockwise rotation is opposed by this frictional force, which will generate anti-clockwise rotation. Okay, and the frictional force that is written over this beneath this particular brake arm happens to be in reversal of this particular frictional force. Therefore, it is going rightwards. So my respected viewers should not confuse over here. And if we just put this shaft back over here, this and this will get cancelled. It would seem as if there is no friction generated, and the system will be in equilibrium. And so now we will solve for this. The lever system is in equilibrium at the verge of rotation. Now sigma mb equal to 0. Okay, we will take moment with respect to this particular point. What we get? Minus 65 into 4. This is 65 into 4. The distance is 4. It is trying to rotate in anti-clockwise direction. Okay, it is trying to rotate the lever arm in anti-clockwise direction with respect to B, and RC has a moment effect like this in a clockwise direction. The moment arm is 1 meter as given by the problem, and the frictional force will also have an effect because it has a moment arm equal to the thickness of this or the height of this brake lever, which is equal to 0.7. Therefore, and it will have a tendency in anti-clockwise direction with respect to B. So we will equate them equal to 0 because it is in equilibrium. Now 0.272 RC will be equal to 260. Therefore RC equal to 361.11. So we have found out RC. Therefore we will be able to find out this particular frictional force, which is equal to 0.4 times RC. Yeah. So 0.4 times RC equal to 144 Newton, 144.44 Newton, and this is the free body diagram as far as the shaft is concerned. And this is the moment arm, which happens to be the radius. Now, therefore, the torque generated by this frictional force is 144.44 into 0.8 equal to 115.55. We need to understand as to what torque is. And if this is the shaft written in a longitudinal direction, and this is the plane which is perpendicular to the axis of the shaft, okay, and if this is the vertical column, okay, let us say square column, then if this is the longitudinal axis, this is the torque. So torque is also a moment, of course, but it comes with a great difference. The torque will always act on a plane which is perpendicular to the longitudinal axis of the component. So here it is the shaft. So torque has a very tortuous effect. Okay, torque will torture a component, physical component, be it shaft or be it column or be it anything. A line which is drawn like this, I want to explain to you, I want to bring a clear difference between torque and the moment. And if there is a line drawn like this on the surface of the shaft, upon applying the torque, it will take some kind of a helical configuration. It no longer remains to be straight. It will take some kind of a curvature like this. Here also you can just view the effect of this particular torque. So it will be twisted. So there is some kind of a squeezing. Okay, when we want to take out the water in a wet cloth, we will apply the torque to squeeze the water. Okay, therefore there will be a complete distortion, complete disfiguration of the component. So torque is always dangerous because it acts on a plane which is perpendicular to the longitudinal axis of a component. So here it happens to be 115.55 Newton meter as far as this shaft is concerned. And you should remember, as far as this problem is concerned, the root cause of this torque is the frictional resistance that is developed between the interface of the lever arm and the shaft. Yeah. Example 7, and this may be the last example. Okay, this is good enough, and our respected viewers should be able to solve any of the problems that may crop up, that may come up. So find value of P. There are three planks of wood, let us say, which are being piled. The top one is held against a wall with a wire, and here is another plank in between this plank and this plank. Now the question is, find the value of P that is required to cause impending motion for 50 kilonewton block. Okay, what is that force P which will create some kind of a jerk in the leftward direction? Okay, now we will write and the frictional force is also different because maybe materials may be different or the surface reference may be different. So here it is 0.3, here in this interface it is 0.4. Now it is enough if you write the free body diagram of this particular block, because we need to find the force P. Okay, and we need not have to find frictional force that is being developed over here. Okay, so the force P is directly related to the weight of this. Okay, so this is the normal reaction. This is the normal reaction coming from the top block, that is it should be 100 kilonewton. it should be 100 kilonewton, because if you write the free body diagram of this particular block, there is tension going like this, and there is a vertical force going like this, okay, and there is a frictional force which is going in the rightward fashion. And if you apply sigma Fy equal to 0, there is a normal reaction. So normal reaction going up minus 100 kilonewton equal to 0. Therefore normal reaction will become 100 kilonewton, and when we write this free body diagram, it will be reversed. Therefore this will become 100 kilonewton. Yeah, this is the frictional force. Since it is showing the tendency to move leftwards, the frictional force is 0.3 into 100, 30 kilonewton. And at the bottom also, frictional force as far as this block is concerned will be developed like this. It is 0.4 into 150, because the normal reaction over here is 100 from the top plus 50 kilonewton, which is the weight, like this, which is 50 kilonewton. So if we apply sigma Fy equal to 0, again for this block, what we get is this normal reaction going up minus 50 minus 100. Therefore normal reaction over here will become 150 kilonewton, 100 plus 1 plus 50, and accordingly the frictional force will be 0.4 times 150, 60 kilonewton. And if we apply sigma Fx equal to 0, we will get back as to what is the force that is required. What is the force that is required, which is nothing but the summation of the frictional forces, one developed at the top, one developed at the bottom. Therefore P happens to be 90 kilonewton. It is equal to 60 plus 30. We will write P minus P equal to plus 30 kilonewton plus 60 kilonewton. So when they are sent that way, the equation that we get for sigma Fx equal to 0, we will get back P equal to 90 kilonewton. I have not written the equation here because it may look very primitive, okay, and that is the thing. And with this we complete. We have solved 7 typical problems which comes from the first kind of problems, that is on friction, that is friction that is developed on horizontal surfaces. And we have seen at least 7 kinds of systems, okay, and the situation for that particular system to develop at some interfaces where the frictional force happens to be horizontal in nature. Therefore the problems are so called. So we close this tutorial, and if you liked this tutorial, please subscribe, and the next tutorial will bring out the friction problems or the friction forces that are developed on inclined planes. Until then, bye. Thank you.